Okay, thank you very much, everybody, for coming along. We've got two seminars today from two of our colleagues, and they're both going to be really covering marine renewables in some sense. And the first person who's going to speak is Mark McAllister, who's in his first year as a PhD student and with his undergraduate degree here at Edinburgh. And he's going to talk about, well, very large waves and what happens when they impact on the marine energy resource and how they affect the devices, and he's supervised by Becky. Thanks for this question, Jason.
Just so everyone's aware as well, there are recordings today coming out for MASTS.
Okay, so as Alex just said, this is my title, Classification and Characterisation of Extreme Waves and their Impact on Marine Energy Device Development. Does this work? All right. Okay, so yeah, I'm originally from Aberdeen. This is a bit of background. There's a picture of the harbor. As Peter McCallum suggested, I probably should have a picture of someone getting attacked by a seagull, but I couldn't find one. This is me. I graduated in Edinburgh last summer, and I liked it, so I came back, and I've been at IES since October. So it's about 5 or 6 months of full kind of finding the feet, and just a bit of general interest. I like lots of sporty things, but this is a picture of me wakeboarding. I'm a member of the University Club, so if anyone ever wants to come and give it a shot, just let me know. Right. So extreme waves kind of go by a few different names. They're sometimes called rogue waves, freak waves, abnormal waves. But in this circumstance, they all mean the same thing. The general definition of a freak wave is a wave whose height, significant wave height ratio, exceeds an amplification index, or crest, the significant wave height ratio, exceeds the crest amplification index. And generally, these are regarded as 2 and 1.3 respectively. And these are derived from the 99th percentile probability for a 20-minute sea state modeled as second order. And then this graph here shows the Druckner wave, which was one of the first recorded freak waves. It was recorded on New Year's Day, and it's also called New Year's wave for that reason, in 1995 in the Norwegian North Sea. So there are broad implications of this kind of research. First of all, freak waves, despite the name, aren't actually that rare. They've shown off the coast of Brazil that they occur about 3.7% of the time. This was because there was about 700 data sets considered, and of those, about 250 of them contained freak waves. So that's fairly common. So it makes them quite an important consideration when developing and designing marine energy devices. And also, any increased understanding in these waves would potentially allow for some kind of active device response, so they can actually protect themselves and assume a protected position if a wave was detected. And also, there are areas that have a particularly high risk, and the North Sea is one of them. So that means any development in the North Sea really should consider this. And this image here is a Norwegian container ship which got struck by a freak wave, and the damage is quite obvious. Cool. So my initial aims are to kind of characterize freak waveforms with the relevance to marine energy. Firstly, I'd like to kind of see if I can group them into any categories, so this is kind of establish the different mechanisms of waveforms. Secondly, I'd like to try and look at the 2D and 3D geometry of these categories, and then third, look at how they evolve over time and then propagate. So the data I'm going to be using is probe data, which is taken from the North Sea, and then this here is a 20-minute sample, and they come in 20-minute samples. This one happens to contain a freak wave, and then this is the freak wave profile here. So first of all, I said I kind of want to try and group them, and I'd like to try and group them into different waveforms, or what I would call mechanisms. The first of this is directional multi-wave interaction. Now these kind of exhibit themselves as waves with a pyramidal shape, a very short crest, and then in a spectral sense, they're quite broad-banded and they have high directional spread. So these kind of waves will appear and then disappear very quickly, which probably makes them quite difficult to detect in advance. And then the second type of waves I would call grouped waves that form through modulation instability. Now these waves are longer crested than what you can call a fabled wall of water, kind of seen in the tail, really long waves, very high. And then these would have a narrower banded spectrum and a low directional spread. And because of that, they can kind of be considered almost unidirectional. So these waves would propagate in a given direction, making them potentially detectable. Right, and then to try and categorize these waves, I'm looking at two different techniques. The first of which is called Hilbert-Huang Transform, which is a kind of alternative to standard Fourier analysis, where it's applicable for non-stationary and non-linear signals. And this derives the instantaneous frequency components of a wave signal. And then once you've done that, you can actually plot them on a time basis, and you can probably observe mechanisms through that. The second approach I'd like to look at is actually reconstructing a wave from probe measurements in 3 dimensions. And then once you do that, you can actually visualize the waves, observe the geometry and their propagation. So I'm just going to talk a little bit more about Hilbert-Huang Transform. So what this does is it breaks a wave signal into what it calls intrinsic mode functions, and this is done by a process called empirical mode decomposition. And these are 2 examples here. So on the left, you can see in the black the original wave signal, and then in the color, these are all the intrinsic mode functions plotted at the same time rate. And then you can see here that one of the mode functions pretty much makes up the whole wave signal, whereas here, the wave functions all sum to make up this free wave. So this is kind of an example of a grouped wave formed through modulation and stability, and this is an example of a wave through multi-wave interaction. And then having derived these IMFs, you then perform a Hilbert transform, which converts each IMF into an instantaneous frequency signal. And then having done that, you can plot them like this, which gives what's called a Hilbert spectrogram. With this, you can actually plot against time the frequency and amplitude. And this shows you the individual frequency components and how they interact to make the wave signal. Right, and then a little bit more about 3D reconstruction. What I'd like to do is use the probe measurements I have and then assimilate them and reconstruct them in 3 dimensions using what is called a model based around a higher order spectral model. And then once you've done this, you can actually visualize graphically the waveforms and their propagation, and you can obviously observe things like the 2D geometry, the 3D geometry, and the mechanisms behind it. Then hopefully, having achieved this, I'd like to try and characterize these waveforms geometrically. There's kind of various ways you can go about this. The kind of classical way is looking at the steepness and asymmetry of the wave and plotting that against various spectral parameters. And then the way I kind of like to try it is using proper orthogonal decomposition. This uses a large sample of waveforms and then produces a generalized kind of characteristic waveform for them. So that kind of approach is probably more useful for design considerations because you can recreate that in testing. And then the general kind of aim of this work is that I would like to try and produce information for the design of energy devices and maybe even the control of them that is not easily derivable from time series data, but you can work it out from time series data so you can know more about the way the waves propagate and the 3D geometry that you couldn't easily observe just looking at simple time series data. That's what I'd like to do. I'm not sure how easy it'll be, but has anyone got any questions?
And so when you say the source of data is Waveforms, is that like on platform?
Yeah.
And is it just one single point? Or do you
I have three probes.
Within
Within like about 15 meters.
Okay. And that's what you use to reconstruct it?
That's not bad. This is something that I've just started looking into and interested, but I don't know how possible it is. It's something I'd like to try and look at.
I would have thought the most extreme forces, you're looking at forces on offshore installations, devices, come from the braking effect. So is it not important, not only to look at the height of the wave, but whether it's actually overtopping or not its braking, because that's when the extreme impact forces arise.
It's something that probably is significant and potentially through these modeling techniques I could visualize it. Just now I'm just going to classify these waves in a more general sense. You could work out the different kind of generic mechanisms behind them, but then that is something that could definitely be looked into. It is difficult to, obviously the model might not be able to model breaking waves properly, so it's difficult to kind of visualize. I don't know how you would do it, but it's something that I could look into. I know you can look at it by looking at critical steepness in waves, and if they exceed that, they will be breaking. So that can potentially be a way to look at that.
I know oil companies are working on forces regions that extend to consider units the braking, the large braking waves.
That could be something that's very well, that's
So the frequencies that you said, but they're not actually at freak, but
Yeah.
taking they happen more frequently than the distribution.
Yeah.
That you expect.
Yeah, well, they happen more.
So,
Yeah.
does that mean that probably the distributions are wrong and it's actually fatter tailed?
Yeah, a lot of people, there's a lot, it's not something I'm looking into too much into, there's a lot of work where they look at normal problem distribution and then they tend to kind of potentially out towards the end, and there's a lot of corrections to be made to like a kind of rally distribution to account for the increased probability.
That it's a non-normal distribution. Or related to densities?
Um,
Find any specific depths in the velocity?
Well, obviously with the data I've got, it's a fixed depth. It's something that I had considered looking into, maybe like if I create this, if I get this model working, I can let them propagate the shower depth or something like that. I don't know how you would look at it. But this is a kind of intermediate depth. There's a study actually that shows that a lot of the energy changes as it propagates into shower water, and I can't 100% remember what happened. I think it kind of dissipates in the showing itself. I don't quite remember. Well, I think 3D reconstruction is probably important because, like, it obviously affects the wave. It's a very mirror shape that impacts on something that's maybe like attenuating like this. It might not do too much damage, but if it's a wave like as a flat front that hits on an attenuating device, it could potentially damage it more. That's just, I think that's just something quite relevant to different shape structures. And it depends on the mechanisms of the way devices work, I guess.
Maybe I'll make a comment. Oh, sorry.
Have you looked into wavelet transforms at all?
I have looked into wavelet transforms, and the kind of body of literature suggests that the Hilbert-Huang Transform is a more robust method because there's fewer assumptions made in it, and it gives a similar kind of graphical output. So I think that's why I'm going to go with that one.
If you take a very long series of data from a board and analyze it, and you collect your waves, the extreme one in the center, in descending, the extreme very large, not so large. New wave seems to work very well as a theory to fit it, and that links back to the spectrum. Communicates pretty well with directional. So the only problem with new wave is that it's got some linear assumptions in theory, but otherwise it's just like the other approach that I was familiar with, is using Schrodinger's equation for this kind of problem. And I wondered whether what you're doing would naturally take you towards something like new wave, which is very easy to implement.
Yeah, I've looked into it a little bit, and you said that it's a linear assumption, but there are some like higher order corrections for it as well. I think that's a very difficult kind of thing for designing considerations of modeling forces, and I think the kind of broader implications what I'm trying to do is to work out how these waves are in 3 dimensions, as I said, and also how they propagate, and to see if they can kind of be predicted, and just to kind of go a little bit further than just the simple kind of force measurements on a new wave.
New wave will give you the multi-direction seas, because Paul Taylor at Oxford with Tom Adcock, I've got a couple of papers I did in Proceedings to Royal Society where they apply new wave type approaches, but they look at multi-direction seas. For example, with the Droutner one, by including multi-directionality, they get an interesting thing they can actually work out that wave is the intersection of 2 wave presence.
Really? Okay.
And what they can't tell you exactly the angle, but they can tell you that there are 2 wave frames going in, which is interesting because it's from a single measurement.
Yeah, well, that's interesting because I was reading a paper the other day that said the exact opposite. It said that they took the response of the platform and they thought from the response of the platform they could divide it into unidirectionally. But I haven't read that paper. It'd be very interesting to read that out. Yeah.
And the second thing was just to do with the devices. If you shift your attention from the North Sea to the Atlantic, the coast of Ireland, you find you have these kind of waves appearing almost on an annual basis. And I saw some data that had the state came from a board, and the data had waves of 40 metres high, and they were not disbelieved by the people in Ireland at first, and when they found there was a problem with the board. Once they rectified that, they still found every year they were getting waves over 20 metres high in that, and that seemed to me maybe an even more interesting area than the North Sea.
Right, yeah. It is interesting. I guess I'm just currently I'm just looking at the information I have, so that it's less kind of predicting why they happen, predicting how they happen, what happens when they happen, I guess is what I'm focused on. That's it.
Well, thank you very much. I think, our next speaker is Paul Bonar, and he's going to talk about effective marine energy design subject to social and ecological constraints. And he is in his second year, and he was originally at NUI Galway and came here for the MSc in Sustainable Energy Systems in Edinburgh in 2012, and I think you've got a Saltire scholarship.
Yeah. Want to get this working?
Come on, just that's it.
Yeah, there we go. Sorry, Mac guy. Right at the bottom. All right, right, yeah. Cool, thanks. So thanks for coming along. My name is Paul, and I'm here to talk about my research topic, which is marine energy design subject to social and ecological constraints. So this is a Saltire Prize studentship, one of the part of the ETP's Industrial Doctorate Program, one of a number of activities that supports the Scottish Government's Saltire Prize. So yeah, so just a bit about me first. This is I'm from Donegal, which is in Northwest Ireland, and this is where I grew up, a very, very small town on the coast called Burtonport. I then moved to Galway, where I did my undergrad in civil engineering at NUIG, before I moved to Edinburgh, and I did the MSc in Sustainable Energy Systems here, before starting my PhD. So just to start with the Saltire Prize, as we know, Scotland has massive marine renewable energy resources. Estimates suggest a quarter of Europe's tidal current resources and a tenth of Europe's wave energy resources. The Scottish Government has also got very ambitious targets for renewable energy, aiming to generate the equivalent of 100% of its own electricity demand from renewable resources by 2020. The Saltire Prize is the world's biggest prize for marine renewable innovation, aimed at accelerating the development of wave and tidal current energy. The £10 million Saltire Prize will be awarded to the organisation that generates the greatest volume of electrical output above the set minimum 100 gigawatt hours over a continuous 2-year period using only the power of the sea. So my studentship aims to benefit the marine energy industry by removing or minimizing constraints on future development and supporting effective designs incorporating compliance with social and ecological constraints. So it's about recognizing that there are these constraints on development and looking at how production can be maximized within these limits. This involves investigating present theories on optimal marine energy design and trying to validate some of these unknowns if there are any. And it's supervised by and directly supports the work of the Saltire Prize competitors, which are 5 companies: Aquamarine Power, NHN, Pelamis, Scottish Power Renewables, and West Isle Tidal. And these are snapshots of kind of proposed development areas. So the project can be split into 3 different tasks. The first is a review of published work associated with the ecological and social impact of marine energy. And this is just to highlight the biggest issues. The second is an assessment of constrained design practice as applied to marine energy arrays. And this is just kind of highlighting gaps in knowledge that might need to be closed if developments to be optimized. And the third part is an analysis of developing design practices, looking at how we might go about closing these gaps. So I've finished task 1, I'm currently on task 2, so I'll just kind of run through quickly what I've done so far. So as we know, practical marine energy resources are subject to social and ecological constraints, such as conflict with other users of the sea and environmental protection. And while renewable energy is supported by the vast majority of people, reluctance to investment and public opposition to siting decisions remain key barriers to its expansion. And marine energy in particular is then further constrained by the uncertainties regarding cumulative impacts on the marine ecosystems. So some of the reasons for public support for renewables, environmental concerns and ethical obligations to displace fossil fuels and combat climate change, or they may be based on material beliefs that marine energy will create jobs for local workers, promote energy independence, provide cheaper free electricity, and increase local tourism. For some of the same reasons, renewables are opposed. So for environmental concerns and ethical obligations to protect marine life and natural landscapes, or they may be based on beliefs that marine energy will have an adverse effect on local fisheries, navigation safety, marine recreation, tourism, property values, and community harmony. So due to the emergent state of the industry, the ecological impacts won't be fully understood until devices are deployed and their effects monitored. And even then, impacts are likely to vary with location and scale, with the design and scale, with location and season, with the design and scale of devices, and maybe cumulative both over time and with an increasing number of devices. But research suggests that the most significant impacts are going to be flow modification. Modification of waves and tidal currents can significantly alter the maintenance and functioning of ecosystems by modifying things like sediment suspension and transport and altering patterns and rates of erosion and deposition. Also a concern, underwater noise, particularly the sound produced by installation activities, is a particular concern. The sound is used by a wide range of species for communication, navigation, foraging, avoiding predators, and finding potential mates. There's still quite a lot of unknowns about background noise in marine environments, so impact assessments are limited by the lack of information regarding device performance data and species responses. But with larger arrays and extended installation periods, noise exposure and habitat exclusion may become significant concerns. With the deployment of marine renewables, a range of species are placed at risk of collision with moving machinery or mooring lines. The presence of devices might also modify habitat use and migration patterns, and even survival or reproductive rates. Overall risk of collision is quite low, especially for agile species, and it's thought that collisions will be limited to young, old, disease, disoriented, or transient individuals who might not be able to avoid them due to reduced capabilities or lack of experience. So those are the main issues, and just the key constraint that I found is that marine energies, the main barrier is the uncertainty surrounding environmental impacts because of the wide variety of device designs, the lack of baseline environmental data, and the complexity associated with assessing the impact on a range of species. So moving on to task 2, a couple of challenges we faced early on were that they would be looking at optimal design, and we'd be working with 2 wave energy companies, 2 tidal current energy companies, and one which focused on both. And if you've ever worked with a company, you know how hard it is to try working with 5. Of those 5, 2 are device developers and 3 are project developers working with commercially available devices. And of course, theories on optimal system design are commercially confidential and highly device specific. And the devices they use by the companies are so varied that finding a common user scheme has been pretty challenging. So yeah, we figured the best thing to do would be to speak with a spokesperson of each company and determine their research needs, but this hasn't been very easy. I've been stuck on this project for a long time, and but we were eventually able to get some project meetings at the end of January, and now it looks like we might be starting to move again, which is good. So because this next task is about constraint design practice, I read up everything I could find about the design of Oyster and Pelamis, which are the original devices designed by these companies. And everybody knows about these devices, but I wanted to look at why they're designed the way they are. So Oyster is a buoyant bottom hinge flap type device that surges with the incoming waves and pumps high pressure seawater to a conventional hydroelectric plant on shore. It actually developed as a logical progression from oscillating water column devices and the need to reduce the structural size of converters. So after that, the flap type device seemed the most similar, and they demonstrated high capture efficiency in the most commonly occurring low energy seas. For a flap type device, power capture is related to the wave force or wave torque more than incident wave power. And wave force is related to the horizontal water particle acceleration, which tends to increase in shallow water due to shoaling. And in shallow water, so waves lose some of their energy due to bottom friction and wave breaking. But for aquamarine, this small decrease in exploitable resource is more than made up for by much lower extreme loads encountered in the nearshore environment. And Pelamis, as we know, is a semi-submerged, free-floating, articulated structure composed of cylindrical sections linked by hinged joints. Pelamis was designed according to a set of key criteria that the designers thought would be necessary for a promising device. So it's designed to survive before, survival first, survival before capture efficiency. It's designed to reference itself rather than to eliminate the need for an external reaction source. It inherently sheds loads. Its long and sleek shape allows it to decouple from long storm waves and dive underneath wave press when they get too high. And it's designed for a minimum of on-site work and using no fundamentally new components. So yeah, at the end of January, we were able to get a couple of project meetings with 2 of the companies to speak about some of our research findings so far and determine their research needs. What we found was that ecological concerns are not a significant constraint on the industry because environmental monitoring will identify any adverse cumulative or long-term effects that require mitigation. And public oppositions now represent a significant constraint either, because imagined fears fade and perceptions change over time. And of course, they do have to consider wildlife and stakeholders as part of impact assessments, but at the minute, devices are still largely designed as a proof of concept, and there hasn't been much feedback from monitoring studies. Rather than social and ecological, the key constraints appear to be financial and technical, so the project outline may need to be updated to better suit the needs of the industry. So we were able to identify a couple of key research areas, the most interesting of which is interactions between devices and arrays, given the potential implications for power output of project economics. The first movers into the potential for the fact that the first movers into the potential for had to sign up to an operator's agreement and agree not to sue each other if anything goes wrong. Shows that these impacts, these interactions are not fully understood. They do have the ability to veto any new development that they think might affect their own, but this isn't an ideal solution. So I've given how close some of the potential sites are. I think it's definitely worth investigating. And modeling flow, this is likely much more of an issue for tidal turbines, which tend to be located in a resource hotspot. And modeling flow through arrays might also let me have a look at cumulative environmental impacts arising from a number of arrays within a region. But like I said, we've only just identified this topic. It's still very broad, so haven't gone into any great detail yet. But if anyone has any questions or suggestions for me, that's all I have to say.
Yeah. How do you monitor environmental impact of unmarine life?
They do quite a lot with. So that they measure in particular things that they're worried about. They assess it like before they go in, and they measure things like flow change, and they use a lot of monitoring techniques to look at sediment suspension and altered and coastal processes. And they use for marine animals, particularly, they use a lot of marine mammal observers just to kind of spot any changes that are occurring. But the main thing they do is they do quite a lot of surveying before they deploy anything to establish a good baseline of data, and then they continuously monitor afterwards for any effects that come up.
When we're talking about opposition to development of new schemes from the general public, I thought perhaps one of the most important factors was the visual impact.
Yeah.
And this has always been a problem with the, wind energy, for example. And
yeah.
I think it's one of the biggest factors in the people opposing these offshore, especially nearshore, things like wind and or Oyster, etc.
Yeah.
So I just wondered if you consider that, because I know a lot of people are looking into this.
Yeah, no, I had seen that. I've come across that. But in terms of their deployments, which they haven't done any so far, they found that this isn't as big of an issue once construction finishes. They're not as visible as offshore wind turbines. They lie low in the water, and even though they have to have, bright colours or lights to avoid shipping and things like that.
It depends what device.
It does.
Oyster, especially land-based.
Yeah.
The visual impact will be quite big.
Yeah, and that will become more of an issue with larger deployments. But at the current scale, people are quite happy with, or at least accepting of the first few small developments. They find it quite a source of pride, and they don't mind it too much. They make it their own.
I wonder if that's a bit like a wind turbine, so it's partly when the one or two dotted around the country, but when you come to hundreds of them, but that is
exactly, yeah, and it's something that they definitely have to keep looking at. Very important.
so that's just a comment.
No, that was good. No, that's a good point.
You were focusing on your sorry. You were focusing on the rights on infrastructure related to, for example, a 50 megawatt park.
At the minute, it's still very broad. We've only met with 2 companies out of 5. These are some of the issues that we've identified. But ideally, I think it is both. We've kind of seen that for device specifically, there's not so much, but definitely for arrays, for big parts, these impacts would become.
Or when you talk about the landing and the use of the land next to the park, that may be actually much bigger disruption than the device that would be a few meters or more.
Yeah, it's all the infrastructure as well, so that's something that we definitely have to think about, and that would be included as well.
I mean, sorry, can I just go? I mean, that is a good point because a lot of these devices, there's quite a big infrastructure associated. So, for example, the Oyster, you've got to have this pelt and wheel installation on the shore. So it's not just that it's a school. This is where these things come in. You know what I mean? It's not.
Yeah, this is an issue as well with cable landings and things like this, and propagation of a lot of small buildings right along the coast. They're finding this to be quite an issue as well. So, I mean, it is quite important.
Local economics probably come in a bit. Very politely ask one point I think is that if you stand to gain financially from the presence of these devices, it seems the whole attitude changes, and they're very keen to have them as long as they maximise their own personal benefits, and that is actually being to the disadvantage of some device development. Where the device developer cannot anymore finance even the trials because the local farming community and fishing community are delighted to see those sea pounds everywhere, and that seems to be, they made quotes the aesthetic and also the terrible damage to fish stocks and other things, but their main interest seems to be in the financial.
Well, it's the same with the wind turbines, right? If you happen to be in a farm and they're going to tell you enormous amounts to turbine.
Exactly, yeah, it's a benefit of the few that are on the land, I think, as well.
Just to add a comment to Travis, the company's Pelamis and Autonomy, they both sent out questionnaires, similar sort of things to public stakeholders and local councils about the visual impact. The answer they got, that's nothing to worry about. They are okay with visual impact because they have low impact.
Yeah.
And even if the parks will be developed, that will be a different story. But assuming there will be parks developed, what they thought, it's not going to have a serious impact on, the visual.
Yeah.
So that point was pushed down, and that's all.
Yeah. It's turned out to be not such a big of an issue for now.
I think I can answer that point. I think your point is exactly right, but I think that the reason that what Paul is doing is responding to the survey from the company, which is part of the Saltire Award, so it's the company's view, whereas there may be another view that actually the environmental impacts, for example, may be much more severe, but the company's case, particularly the way energy converter, it's only one company that did get to see the end, and view others, but it's not really a problem. It's
in the plate and
I think if we're done in the room, we also just have had a text to say there's some questions online, so we'll see if this works. But, John, do you want to let us know your questions?
I've got a couple of questions from Ben Wilson at Sounds. His first question for Paul is, basically he says, is the constant surveying being conducted in Scotland actually providing the information needed to make, one, consenting decisions, and two, understand mitigation issues?
Yeah, I mean, there is quite a lot of monitoring studies done for this, and they tend to these are still quite small developments, so there's still quite a lot of unknowns, but so far the consenting has been fairly straightforward. They've identified some issues, and they've just their approach is to survey, deploy, and monitor, and that seems to be going quite well, at least at this scale. That's a couple of device deployments that have been done already.
Okay, that's great. And we actually had a question as well for Mark, which came in just after his talk, from Philippe Glison, and basically he's interested in knowing where you get your data from.
So the data is acquired from the North Sea. I'm not actually fully in control of it, so if anyone wants to speak to anyone about it, I have to speak to my supervisor, Venki. Is that okay?
Yeah, that's it. Thanks a lot. Thank you.
Okay, thanks, John. Is that all the questions?
Yes, yep, that's everything.
Okay, thanks very much.
Thank you.
I'd like to just say a big thank you to the two speakers. It's quite an